A very warm welcome, dear students. In today's video, I will talk about electric field, superposition principle, and the electric field lines. Now, without wasting much of time, let's get started and try to understand what is an electric field. Electric field due to a charge is the space around the charge in which another charge can experience a force of attraction or repulsion. So what exactly I'm trying to say is that if you have any charged particle, let's say I have a charged particle Q over here, and I try to bring another charged particle near it. So this Q naught is like a small test charge which I'm trying to bring near the plus Q charge. When I do that, this test charge will experience a force. Now whether that's force of attraction or repulsion will depend on the signs of the charge. Further, if you talk about electric field, theoretically electric field can extend up to infinity, but practically it will never extend up to infinity because there would be lots of obstructions in its way. Thirdly, the strength of electric field generally is described as electric field intensity. So if we ask you to calculate the electric field intensity at a point, we are just asking you to calculate the electric field. And another thing is that for electric field also follows the inverse square law. That means the electric field at any point is directly proportional to 1 by r square, or you can say it is inversely proportional to the square of the distance. Now moving on, let us try to understand how to define electric field in a quantitative way. See, physically it is just a space around a charged particle in which another charged particle will experience a force. But quantitatively, electric field intensity at any point is defined as the force that is experienced by a unit positive charge. If I talk about electric field at any point, then that would be equal to the force divided by the charge. In other terms, I could also say that the electric field for a point charge is simply K Q by R square. So this Q that we are talking about is basically the source charge. Source charge means the charge who's going to produce in the electric field. Further, over here, the main idea that is happening is that let's say that I have a charge Q and I want to figure out the influence of this charge or the electric field due to this charge at a distance r from it. Let's say that this is point P. So the electric field at this point P would be given by KQ by R square. And therefore, we say that electric field obeys the inverse square law. Also, if you talk about the force over here, force would be measured in newtons, charge would be in coulombs, therefore the unit of electric field would be Newton per coulomb. You can also say that electric field is measured in Newton by coulomb. That's one and the same thing. Also, from here, you can see that your force and electric field will be in the same direction if your charge is positive. If the charge is positive, then the electric field and the force will be in the same direction. If the charge is negative, then the force and the electric field will be opposite to one another. Both of these are vectors, therefore associating a direction with them is very important. Now K over here is simply 1 by 4 pi epsilon naught, which is equal to 9 into 10 to the power 9 Newton meter square coulomb minus 2. From here, the main thing, the most important point that you have to keep in mind while writing the electric field due to a charge is that the electric field only depends on the magnitude of the source charge, not the test charge. You may bring a very small charge, you may bring a very large charge, but the electric field is always produced by the source charge. So therefore, its magnitude will depend only on the source charge itself. Further, let us try to understand a few more things about the electric fields. So electric field obeys the principle of superposition. Principle of superposition is also valid for Coulomb's law. So basically the electrostatic forces. Further, what does this principle of superposition tell us? So principle of superposition simply states that the electric field at any point due to a group of charges will be equal to the vector sum of the electric fields that are produced by each charge individually at that point when all other charges are assumed to be absent. So for example, if we look through this diagram, I have a number of charges over here. I have Q1, I have Q2, I have Qi, and so on. I can go till Qn. I want to find out the electric field at this point P. So the electric field at this point P will be equal to the vector sum of the electric field due to the charge 1 plus the electric field due to charge 2 plus the electric field due to charge 3, and so on. You can add all the fields till the nth charge. The only thing that has to be kept in mind while using the superposition principle is that because we are dealing with vectors, electric field is a vector. Therefore, it is very, very important that we only follow the vector addition rules. We do not treat electric field as a scalar. So when you add, you have to take the directions into account. Now, we will do one question here on the superposition principle in order to understand how to apply the directions here. So I have 2-point charges QA equal to 3 microcoulomb and it's located at 20 centimeters from QB, that is minus 3 microcoulomb. What is the electric field at the midpoint O of the line joining the two charges? If a negative test charge of magnitude 1.5 into 10 to the power minus 9 coulomb is placed at this point, what is the force experienced by the test charge? So in order to understand this, the idea is pretty easy. So let's say that I have this QA charge at point A. I have another point B, and on this point B, I have the QB charge. Now this QA and QB, they are separated by a distance of 20 centimeters. And I want to find out the electric field at a point P or at a point O, which is at the center of this. That means the distance from each of the two charges here is 10 centimeter. So in order to find the electric field due to A and B, I can simply use the formula that we wrote. So the electric field at point A will be equal to KQ by R square. So K we know is 9 into 10 to the power 9. And the value of charge over here is 3 microcoulombs. So 3 into 10 to the power minus 6, because I have to convert the microcoulomb into coulombs, divided by the distance, which is 10 centimeter, and in meters it would be 0.1 meters. So 0.1 square. When I substitute this value on the calculator, I get this electric field as 2.7 into 10 to the power 6 newtons per coulomb. Now, this is just the magnitude of this field. What about the direction? Since QA is a positive charge, for a positive charge, the field is always outwards. The field always starts from positive charge and moves outwards. Therefore, due to this A charge, the field at this point A would be away from it. This is the direction of electric field due to the charge A at point O. So I can very easily say this 2.7 into 10 to the power 6 Newton per coulomb is in the right direction. Similarly, the electric field at point B, like electric field due to B at this point O, would be equal to KQ by R square as well. And since the magnitude of B, the charge at B, is also 3 into 10 to the power minus 6, the distance is also same. Therefore, this force would also have a magnitude of 2.7 into 10 to the power 6 newtons per coulomb. Now, the question that arises is that what about the direction of this one? Now, for a negative charge, the direction is always towards the charge. For a negative charge, the direction of field is towards the charge. Therefore, the direction of field at point O due to this B charge will be towards the charge. So this electric field due to B charge is also towards right. Therefore, if I want to find out the total or the net electric field at this point O, it would be simply the sum of the electric field at A and B. Why am I adding these two? I'm simply adding these two because they both are in the same direction. So 2.7 plus 2.7, that gives me a value of 5.4. So 5.4 into 10 to the power 6 newtons per coulomb, and this one is towards right. It's towards the right direction because both the electric fields were towards right. This is all about the A part. Now for the B part. In the B part, I am supposed to find out the force. Now I know that the force and the electric field are related to one another. Force is Q times E. So the charge value that they gave us over here is 1.5. It's a negative test charge, okay? So I can also write it as negative 1.5 into 10 to the power minus 9. This is already in coulombs, times the electric field, which I have found out to be 5.4 into 10 to the power 6. So if I calculate this force, this comes out to be 8.1 into 10 to the power negative 3. Now what about this direction? This charge is negative, therefore the direction of force would be towards left. For a negative charge, the force and electric field are in opposite directions. For a positive charge, the force and electric field are both in the same direction. Okay, so this is all about the superposition principle, and this is how you apply superposition principle for multiple charges. Now, we further move on to the electric field lines or electric lines of force. We will try to understand the characteristics of the electric lines of force. So firstly, an electric line of force or an electric field line, what does it show you? It is the path along which a unit positive charge would move if it is free to do so. So electric field lines are simply showing us the direction or the path that is followed by a positive charge. Secondly, these lines will always start from a positive charge and end at a negative charge, as I told you earlier as well. Thirdly, these electric field lines never pass through a conductor. Now, they never pass through a conductor because of the fact that the electric field inside a conductor is zero, always zero. There cannot be any electric field inside a conductor. Why it is like that? The reason for that is that all the charges in the conductor reside on the surface. There is no charge inside it. So therefore, there is no electric field inside the conductor. Next part, these field lines will never intersect because these are showing you the path of a positive charge. A positive charge can follow only a single path at any point. At one point, you cannot have two different paths followed by a positive charge. So they will not intersect. The more crowded the field lines are, or you could say the more closer the field lines are, stronger is the field. So the part where there are multiple field lines crowded together, that has showing you a strong field, and if they're away from one another, then that shows you a weak field. Over here, I have certain diagrams to explain you field lines better. Let us look at these one by one. So for example, if you see this red charge, it's a positive charge. For a positive charge, as we can notice, the field lines are moving outwards. The blue one is a negative charge, therefore the field lines are towards it. So for a positive charge, away from it. For a negative charge, towards it, always. Then this one shows the electric field due to a positive and a negative charge, which are equal in magnitude. So this is basically talking about a dipole. So for a dipole, you can see that the electric field lines are originating from the positive charge and they are ending at the negative charge. Then the third diagram is showing me two positive charges. These are the field lines due to both of them. In the center over here, as you can see, there are no field lines because in the center over here, the field lines due to both of these cancel out each other. Therefore, there are no field lines in the center. Now, a very important point. See, electric field lines are imaginary, so you won't be able to see them. But electric field is real. To represent electric field, because it's just a space, it's just a region, we make use of electric field lines. So they help us represent a field. With this, we are done with the basics of electric field. In the next video, I will talk about the electric field due to an electric dipole. We'll do some derivations, so stay tuned. Thank you for watching and don't forget to subscribe, share and like.